Okay, hello everyone.
Good evening.
Okay. Hello, everyone.
Okay, we have about 10 people signed in right now. Expecting we'll get about that many here in a few minutes. Okay.
Good.
Hello, everyone. Joe and Squim here. Can you?
Hi, Joe and Squim.
Hey, yeah. Hey, this is really great. I just wanted to chime in real quick. Yeah, this has been certainly worth it. Although I miss coming out to Portland, eh?
Yeah, it's more fun in person, for sure. But we definitely need to find a way to record our future in-person meetings as well.
Right.
Because because I think the real value that we've discovered this year being on Zoom is having these recordings is really going to become valuable over time.
Yes. Well, that's good. Well, I hope everybody's doing okay. And Richard, doing okay?
Yeah, I'm not sure if he signed in here. Yeah, there he is.
Richard, yeah.
In. Yeah.
He's probably getting his audio to work.
Mm-hmm.
I was just through Hood River, spent the night, came back from LIGO, finishing up those actuators. And went to the that museum over there. That was really nice. The Aviation Automobile Museum.
Oh.
Excellent.
Very good. So how's LIGO up and running right now?
No, they're actually down for maintenance and virus. But the project was delayed because of the virus and also some engineering problems. But we finally got approval to go over there about a month and a half ago. And my son and I spent, we went there 3 times for about a week each, 4 to 6 days, and completed winding and assembling the electromagnetic actuators for the A+ upgrade. So, and I'll probably continue to do little projects with them for quite some time, it looks like. But it was fun. And since the observatory was down, we ended up getting a nice tour of the LVEA, the big building. I haven't been inside in years because of the anytime they're operating, you can't go in because it makes too much vibration.
Oh, sure.
Yeah. So, but yeah, it was a very successful project. We were concerned for a bit. You remember I brought the actuators over. I think it was last year. I brought one. Yeah, the little electromagnetic one. And Dan helped me out with some ideas about winding coils and such. So it was, yeah, it worked out.
Okay.
All right, you're getting some people piled in here. I'm looking right now.
Yeah, we got about 16 now.
Russ, yeah. Hey, Dan.
We'll give it another minute. Well, we'll start at 5:03. That's not too late.
Yeah, I was actually looking for it. Didn't see it. So I just went something.
And then there's all that thing, all the ones that y'all like.
That's what I was thinking from there.
These.
I'm using that one.
Okay. Yeah, all those in there.
All right, let's just go ahead and get started. Yeah, I think we certainly have enough people now. So just to review what we'll be doing in our final session for this year's AltAS workshop, we'll start off with Mel Bartels giving us an update on his 25-inch telescope and how that has worked for him over the last year. And then Russ, Dan, and Dave Rowe will talk about their robotic Speckle telescope project that they've been working on and have up and running. And then instead of a break, Dan asked for 5 minutes to give a short update on Jimmy Lowry's 36-inch scope design. He took some of our advice and suggestions from a few nights ago, and he says he has something of a breakthrough on the altitude direct drive motor. So I'll look forward to that. Then Ed Allen will be back online with his updated clutch system on his 24-inch Elvira telescope. And then we're going to end the conference on something of a really cool video. I received this yesterday and I reviewed it. It's from a group called the Next Generation Telescope Program at TNO, which is an acronym for, that is a Dutch for some unpronounceable word. And what makes it really interesting is that, as you most all remember, that the ALTAS workshop was started based on the idea of looking to what the professional telescopes have come up with in terms of engineering and optics, and seeing what we could find in what they've done that we could simplify and bring down to 1 to 2 meter telescopes, stuff that we and small institutions could build at a reasonable cost. Well, this is something going the other way. As many of you remember, Don Peckham gave us a great presentation, I think it was last year, about his 10 Seggerty telescopes. It was very interesting. Maybe it's 2 years ago now. And it's a very different way of looking at how to build a lightweight, portable telescope structure. Well, what makes this very interesting is that this program in the Netherlands found Don's presentation. They've been communicating with him, and they're looking at using that at a professional level. So I think we'll find it's a 25-minute video that we have, and we'll end up with that. And I think what we'll do is any questions or comments that people have about the video, send them to me, and then I will forward them on to the director of the program, and then I can post their replies to everyone here on the list. So, with no further ado, well, we got 2 more people waiting to get in. We'll let them in. Okay, now with no further ado, we'll go ahead with Mel and his update on its 25-inch.
Thanks, Howard. Mel Bartels here. I'll share my screen. You can see a picture of Andrew Common here. So my presentation is on 25-inch meniscus telescope, an update. There's 2 types of updates or lessons. The first is the immediate one. Does the telescope focus? Sometimes yes, sometimes no. Does the telescope balance? Sometimes yes, many times no. And then there are a deeper set of lessons after you become intimately familiar with the telescope and using it. Some stuff turns out to be really nice and sweet, and other stuff begins to nag at you, maybe a sharp corner that always cuts into your palm when you're putting the scope away that you want to make a change on. So the hero for tonight is Andrew Common, and you'll hopefully see why in a moment. He became interested in the new technology of film photography and wanted to photograph the sun and moon and planets and stars. And he quickly discovered that aperture was needed, lots of aperture. He went to a 5.5-inch refractor, and then from there, he began grinding a 17-inch. And he set that aside to get an 18-inch from Culver, and we'll go down here. There we go. That's the 18-inch in his garden observatory. That was so successful, he then commissioned a 36-inch from Culver. And with that, he took a series of astrophotos of the Orion Nebula that won him the gold medal and became something of an astronomical historical moment because it changed the direction of astronomy. People could see the potential and power of astrophotography to capture the sky. But that he did not stop at. He went on to a 60-inch, which he decided he would grind himself. And the first 60-inch turned out to be a failure. It had astigmatic stars. So he had to think and decided to try again. And the second 60-inch worked. We had perfectly round stars. However, it was so far up at the eyepiece and camera that after a near fall, he switched to a Cassegrain configuration and never quite got that to work. So the scalp fell into disuse. It eventually became the Harvard 60-inch and then moved to South Africa, where it became known as the 60-inch Rockefeller. His 36-inch was owned by an English doctor, Crossley, and then it became the Crossley telescope at Lick Observatory. So being a really smart person, I'm sure he knew that his efforts were ambitious and were likely to fail many times before he succeeded. And he used introspection and review to make improvements. And I would suspect he was also fearless. We heard from someone earlier, Zane Landers, who impressed me as someone who's fearless. He expects to fail, but he is so keen to improve and improve and improve and improve. It doesn't matter where you start, because where you end up with is success. In the business world, we use a technique called the retrospective to build high-performing software teams. The idea of the retrospective is that regular heartbeats every 2 weeks, we get together and sit down and talk about what's going well, what we want to continue, what's not going so well that we'd like to stop, and then identify 1 or 2 improvements or behavioral changes in the process so that we can get better. There is one rule in a retrospective, and that is that everyone's doing their best and it's not anyone's fault. If software is being pushed out that's buggy, well, maybe the developer's being too pressed, or maybe they, in the process, aren't given time to do the validation and verification. Maybe the project manager is confusing about what they want. Maybe the IT manager is pressing everyone to go faster and faster. Or maybe the process is just too brittle and doesn't allow for natural human error and variance to occur. Well, there's also retrospectives for personal use. One I like is the concept of what I like, what did I learn, and what did I lack? So the idea, again, is it doesn't really matter where you start because you're going to make so many improvements. Where you end up is somewhere way out there. However, improving does mean doing something new that you've never done before. And that's where the fearlessness comes in. So it takes time to get to know a telescope, how it performs in a variety of circumstances and a variety of objects, and that's what I'm going to talk about here. So the good. So on nights of seeing, when the mirror is cooled, the views are breathtaking, both super wide angle and high power, both peak observations and the nightly long haul of observing over and over again. Jeff Baldwin has coined a term for these telescopes, Laffert's large aperture, fast focal ratio telescopes. But like Common, I built the scopes with really an observational purpose in mind, and that is to continue on with my discovery of integrated flux nebula or galactic cirrus. So the big question with the 25 inches, would I discover IFNs? I was a little concerned because the IFNs are so broad and diffuse, maybe I would just peer right past them, and the 25 would be a failure from that viewpoint. Well, here's the Whirlpool M51. Well, Leif Howard with his incredible, certainly gold medal from the Royal Astronomical Society award-winning effort on the sketch of the galaxy itself. But I'm concentrating on the wide angle degree perspective, and there are IFN here, galactic cirrus, so I can see that the 25 I could not see through my smaller scopes. Most impressive to me is the Andromeda Galaxy. Normally it's considered too big for a 25, but there's all these faint regions that come off it. I've looked at it enough. And in fact, this view now has become my test for transparency. If I don't see something like this through the telescope, I don't consider it a very transparent night. And I've learned to see a lot of this in my smaller scopes too. So big success on the 25 on that viewpoint. The meniscus shape removes the need for all that rough grinding. The mirror's 25 pounds or 11 kilos, and it's something that you can handle. The entire telescope weighs 75 pounds. I'm actually bending over slightly when I look at the scope near the zenith. I see, after using the scope for a while, opportunities to lessen the weight even further. I think I could cut another 5 pounds, a couple kilos off the weight. I've gradually evolved an observing technique where I do not fix my eye just off center and leave it there. Instead, I move my eye around every few seconds after I accumulate a view. And then I move the scope around to create a larger virtual field of view to increase the perspective of the overall object. Well, to do that, when I'm near the zenith, I need a third axis. I was just using the 10-inch the other night, and all 3 objects that I targeted that night went right through the zenith. And you know, you're twisting around in azimuth, trying to figure out where you need to be so that you can drop the scope a degree or 2 in altitude so that the red dot finder works so that you can go see it through the eyepiece. So I really miss the 3-axis mount. Now, I've been criticized that that stupid Bartels, doesn't he know that if he would just wait an hour, the object would clear the zenith and then he could observe it? But that misses the point. The point is to have natural movement near the zenith. And that's best done by an altitude mount. An altitude azimuth begins to lag up there, and you want to have a natural transition between the 2 motions, alt as and alt out. So the 3-axis mount is a huge success, and I'm certainly going to do that again and retrofit it back to my other telescopes. The blank started as an overslumped f2.2. Greg Willite, who slumped the mirror for me, became super enthusiastic. And when he opened up the trunk of his car to show me the mirror, he said, "Now, I just want you to know, you really wanted a slumped f3, so I figured you'd want a slumped f2 even more." And so it took a lot of effort to get it to where it was. But I did demonstrate to myself that simple mirror on top of a full-size pedal tool did work. So I'll take just a moment. The first parabolization attempt, which I don't really call a serious attempt, I just let the polishing machine run for about 20 hours. I just wanted to see if I could parabolize 60 waves. And I actually over-parabolized the mirror and it was smooth. So I thought, aha, I can do this. So I came into the real parabolization and thinking, okay, this is going to be pretty straightforward. What a miserable experience. I was just chasing zones. A zone would start at the 50% spot, and then it would move out to the 60, and then to the 70, and then I'd corral it, and then it'd go back to 60, and then it'll go back to 50. And it's like, okay, I've been here several times before. And I came pretty close to giving up. And finally, in frustration, I said, I'm going to just treat this like a 6-inch, and the zones will not exist to me. I would just pretend they are not there, and they magically went away, and I was able to, on the next and final parabolization attempt, get a smooth figure. So that's what I've been using subsequently. The other thing that's proved to be really successful is I needed a testing regime to fit the process. So one of the aspects of mirror testing that we debate a great deal about is, well, how good is that test and what does it do? Well, coming from the software world, testing, and there's 2 types of testing, validation and verification, are always in service of something. What I need is to be able to test the mirror, give it a quick dry, get it on the test stand, and at a glance, did I make it better? If so, I'll continue. Did I make it worse? Oops, then I'll stop and retool. And I need to see that instantly. And so my Ronchi test that I do, where I look at the proportion and the smoothness of the curve, that works really well. And then periodically, I can match it up and see how I'm doing in terms of the overall correction. And then I use the star test to coast into the final point. So that worked really well, and I'm doing that again. The wire spire for something this large and heavy, it's several pounds there for the diagonal. That turned out to be a huge success too. Once I collimated the telescope, I've not touched it again. And I thought quite a bit about it. You know, Zane made the comment, he regards optical alignment at F3 as easy. I'm not sure, I think it's easy with a capital E, but it is easy, definitely easier than what you might think if you just sit down and begin to think of the horrors of collimating such a fast scope. And I've come to realize that what's really happening is that once you get that primary mirror aligned and get its axis aimed up the center of the focuser, then it's just a question of adjusting the diagonal. And I've experimented a little bit with misadjusting the diagonal, and it does not seem to affect, with the coma corrector in place, the image as badly as I think it might. So there's something about pinning down that primary mirror and getting it right up the middle of the focuser axis. If you can get that and achieve that, then you're really home. I use Aurora Precision from Nate Courier truss tubes. They snap into position perfectly every time, and I've just never had to realign the scope since I got it going on that first night. The ugly. Well, I chase stones back and forth one way and then another. If you are of my age, you might remember Keystone Cops when we were younger. Well, that's how it was. And really, I became insane because I was doing the same thing over and over again and expecting a different result. Actually, I was expecting failure and insanity, but anyhow, the final run was no drama. And I look at how smooth these curves are here, and I go, my gosh, you know, I hope I can get the 30s to be this way too. There is a very slight error in the figure that you can see in the star test at high power, in that there is a slight low zone. And if you can see my cursor, you can see how the bands fit down the middle here, but then they scrunch up against the top of the perfect curvature here. This one you can see quite well. Similarly down here. So that shows up as a little bit of a low zone in the star test. But the mirror does snap focus, and it's the best I could do. So I'm super happy with it, regardless of what the rating might be. So the method of the day was to do whatever it took to get the scope to perform. So I didn't stop to do a lot of investigating. If something worked, I just stuck with it. If it didn't, I kept trying again. Well, the mirror cell turned out to be simpler than I thought. I was fully expecting an 18 or 27 point. The 3-point was, well, it was unspeakable. But when I tried the 9-point, I thought, well, this is pretty close. And so I went to those 9 cups, which is more than 9 points, to try to smooth out the bending and shearing between the support points. And that seemed to work good enough, so I left it alone. However, the edge supports, I do 2 edge supports at 90 degrees. It's pretty crude. They are touchy. As time has gone on, I see that when I point the mirror down, sometimes the mirror just gets out of whack in itself. So I give the mirror a kick. This is a term that Swayze taught me on the 40-inch. I don't know if he literally went up and kicked the 40-inch with his foot, but you, in this case, aim the 25-inch up at the zenith, and you make sure the mirror settles in very nicely, and then you slowly move it down at altitude and let it nestle in against the 2-point supports. And the star images are really good until something happens. So that's something to improve over time. The sensitivity to temperature changes, I'll talk a little bit about that in a moment, but that's turned out to be more touchy than I initially thought. One aspect, this scope's at f2.6, and boy, you have to place your eye exactly over the center of the eyepiece at the right location, at the right angle, or you get flaring. And sometimes it can be bothersome, but it is something to be aware of. And at our age, you know, we begin to pick up degradation in our eyes and cataracts. So sometimes I switch over to my right eye, my non-dominant eye, and it takes me a little while to train my eye to look down the eyepiece just so. Magnification is constrained because it's just a 65-inch focal length. So as Barbara would tell you, the dumbbell in Howard's 28 with his 130, let me calculate in my head, 132-inch focal length, 133. Then the dumbbell nebula showed more stars and was a nicer view. So there's that constraint too. And then something happened at Oregon Star Party, which, is a little disappointing because people come over and they want to see the scope and everything, and you want the scope to work. And the scope did work for about 30 minutes, and then it didn't work. And the motions just became terrible, just horrible. And then the next day I took the scope off. Well, it only weighed 75 pounds. So, Barbara and I just lifted it off real quick. And this is what the pads looked like. So the notorious OSP dust got another telescope. So what I did after OSP was I switched half of all the Teflon pads to ball bearings. And so now the motion is much smoother. And if it does come up, it's not near as bad. So something to think about. I made that change. All right. So Pierre came down from Toronto, was eager, and he wanted to see Ellipson Lyra through the scope. And so with lots of bravado, I go, of course, I'll show you Ellipson Lyra. It's wonderful. And I looked through the eyepiece and it wasn't. And eventually came to realize that the rapidly dropping temperatures that night at OSP just caused the mirror to deform. And I began to do some experiments back home, and I cooled the back of the mirror, and the mirror went badly undercorrected, just like it did at OSP. Well, I have a 12-volt hot air gun, and I blew that against the back of the mirror, and the mirror went overcorrected. So other than the fact that, oh, I could actually change the correction of the mirror, what that really taught me is that I need to pick one side or the other. There is no compromise. I'm either going to close off the tube, as we used to do in the traditional Dobsonian with plate glass mirrors, or I go to a full-on controlled ventilated system like Ed Allen is demonstrating. So in this case, it was simpler just to close it all off and see what would happen. And then I began to get good images. So you may know that I sold a 25-inch to an amateur in Oregon who is just so thrilled with it. And he's experienced amateur and he knows how to take care of it. And I did that because I'm really hopeful that the 30s will work. I do hold my breath because they aren't proven yet. But he informed me on the phone that the first object he was going to look at was Ellipson Lyra. And he better see truckloads of black between the stars, or that was it. No sale. So luckily, it was a night of good seeing, and I knew what to do with the temperature on the mirror. And the view through Ellipson Lyra was just wonderful. So he turned around and told me, okay, the telescope is sold. So we went from disaster OSP to exquisite images after that. But that was something to really learn and have the temperature go through these extreme environments. And at home, I just rolled it out of the garage shop and observed with it for an hour or two and put it back in, have these terrible temperature changes. So that's some of the lessons I've learned, the longer term lessons and the retrospective approach. And then with a healthy dose of fearlessness and not hopefully too much ignorance, plow forward. So that's my presentation.
Hi, Mel.
So-
Can I ask you a question?
Sure.
So how do you balance your telescope making work with observing work? I realized that one of the reasons I probably would take several years to do what you're doing or even think about doing what you're doing is because I would hate to waste a night in like a dark place like Oregon Star Party trying to troubleshoot my telescope when I could be observing. How do you balance these two? And you're still a very prolific observer, so how do you balance these two? That's my question.
Well, I'm not sure I actually do. So yeah, how do I balance it? Well, Barbara says it's really clear out. How come you're not out observing? So that helps. The other is that I seem to go through periods. So if I'm making the telescope, first of all, I always have another scope to observe with. But I do put a lot of energy into that. And sometimes I just don't feel like observing that night. And I feel pretty bad about it. But having an observing program helps. And then I go through the period where the scope is there and I'm tuning it and I'm learning about it and I'm fixing it up or doing whatever to improve it. And then I'm in my observer mode. So I feel like there's two of me, two Mels. One is builder Mel and the other is observer Mel. And I go very slowly back and forth every year or two between the two. But I do try to observe and have some scope on hand. I also sold the 13-inch zip dop too, because it just hadn't been used for years, to another amateur who's just thrilled with it. And but I do have the 6 and 10 that I'm observing with right now. But yeah, it's a question of focus, and I'm not sure I really balance them quite that well. So
I have a question for you, Mel. You talked about centering your eye to the eyepiece so you don't see any flaring. Does that depend on the magnification you're using?
Seems worse at lower power. And when I go back to the f2.7, f2.8, and by the time I get to f3.0, there's no flaring. It's something about the eye having to be right on axis. It could be too that I am pushing my pupil and I have to have my pupil exactly aligned with the eyepiece's exit pupil. So it could be that. I don't notice the flaring so much at high power, but it can be bothersome at low power. So as you're moving around, you don't always face your eye squarely onto the eyepiece. Sometimes you kind of tilt it very slightly. So that can be flaring. You got to get your head turned and faced right onto the eyepiece. So it's just something to think about on these super fast scopes.
Okay, interesting. So given the overall success of the 25-inch and how you were talking about your reluctance to turn the two 30-inch mirrors into a binoscope, are you thinking of building a similar version telescope structure around the 30-inch mirrors?
Yes. First of all, I'm so focused on the 30-inch mirrors. In my mind, I was actually dreaming about parabolas last night. So, yeah, so on the 30-inchers, the design of the 25 with the truss tubes has worked out really rigidly. Alignment is not an issue. And, you can scare yourself so easily about these ghosts and monsters and boogeymen, and they just don't show up. So if I were conservative, I would say I'm going to build a 30-inch, and I'm going to continue to use the truss tubes with Nate Courier's Aurora Precision connectors and so forth. But I also need to seal off the tube, whether I put in an advanced ventilation system like Ed Allen has shown is superior, or I just passively isolate it from the air. These thin plate glass meniscus mirrors, when they get this big and thin, they act almost like bimetallic strips. And you need to be aware of that. Just these passive ventilation holes in the back are actually not a good idea. So another idea is just to return to some type of solid tube. And you might remember Steve Overholt's Lightweight Giants, where he used styrofoam tubes. And David Davis has done that too. So the weight of the styrofoam is about equal to those aluminum truss tubes. And the styrofoam, of course, is really cheap. If you priced aluminum tubing, you know that it's an incredible amount of money just for that tubing. So so those are actually the two competing ideas I have.
Okay. Any more questions out there?
Yeah, Mel, are you going to be sticking with the like an all manual, keep it a minimalist design, or are you going to go with any sort of the fancy tracking or anything like that?
Oh, I'm going to get fancy. So, here's my Ed Allen story. So when I started in the 60s, what you did was you grabbed the access lock, which was some type of threaded bolt with a knob on it. And you learned that a high power is shifted the image halfway out of the field. And it always shifted it to the right. And so you put the image to the left and you tighten this, and then it would move somewhere in the center. Then you would let go of the scope because it would literally shake for 10 to 12 seconds. And then woe to anyone who touched the eyepiece. And then you would observe. So when John Dobson came along and I clambered up on his ladder and I looked at it and the stars were drifting, it's like, yeah, it's not tracking, I don't know. But then you touch the tube and you moved it and you go, whoa, no more clamping. This is the way to go. But on my computerized 20-inch, the reason I was able to use it at 2,000 power and then 6,000 power and make the comment, okay, I'm going to drop back down to that lower 2,000 power, is that all motions were motorized, including the focuser. So I'm there struggling with my dust, and I walk over to your scope, and I already knew that you grab that handle and then you move it. And I did that, and it was like, okay, I'm going to have a handle on my scope too. Even if it doesn't do anything, I'm just going to put a handle on there because apparently it does good things for you. But what it really taught me is that a system that's bi-state or one state, where like the Dobsonian is one state, or maybe you can call it two state, where it's either in motion or it's not. But at higher power, need to do something different. And that's what I learned from your scope, and the frustration that my scope sticking at higher power is that I really need to have a spectrum, some type of way of altering the friction. But it can't be so light that when I pull out a monstrously multi-tonned eyepiece, you know, that the scope loses pointing, just when I'm going to zero in at high power on Andromeda's parachute or something. Although that one is an easy star hop, there's others where it's like, please don't let it slip, because I spent 20 minutes finding this, you know, field. So now I'm going to do something fancy, and because I think that's a definite improvement.
Anyone else? Okay, well, thank you, Mel. That's very interesting. You know, using looking through your scope at last year's OSP was a real treat. And I totally get what you mean about the clutch handle on Ed's scope. That's pretty awesome clutch system he has. And having a handle like that, whether it's got a clutch attached to it or not, is a pretty good way to move a scope anyway. So next up is Russ, Dan, and Dave talking about their robotic Speckle telescope project. So if those three guys are all here.
We're here because we're not all there. That's what the folks said at the mental institution.
Hi there, Russ.
Okay, well that's physical attendance is plenty good enough for us now.
Oh, okay. Well, I'm going to start just with a short talk about the telescope itself, and then Dan, are you good with talking about SciTech ZWO cam?
Yeah, can you hear me okay?
Yeah. So then, and then Dave's going to wrap it up, because the real intent of this project is not so much 11-inch telescope at my place, but to do automated speckle on larger telescopes like in Chile, things like that. So let me just jump into, let me share screen. Okay, share. Okay, and we'll get the full view here. Okay, everyone see that okay?
Yeah, looks good.
Okay. And so this started out as a project. My Mead 10 had just over the years got worse and worse, and it sat there for I don't know, maybe 3 or 4 years just gathering cobwebs, and I wasn't using it. And I decided I wanted to, but telescopes, as we all know, it's like malaria. It's a disease you never get rid of, and that you may die down for a while, but it'll come back. So I wanted to do another telescope. And after doing Big Woody, which was the 1.5 portable telescope, which was less than a total success, and a light bucket, thought I'd take a different approach and see if I could do a telescope that a little more conventional. And I thought about different mount things and decided to go with an L mount. So this is an early sketch of the telescope, and so I just don't do drawings at all, and well, a student at Cal Poly signed up on the project to do SolidWorks. So this is in SolidWorks, and so this was implementing in SolidWorks. And some of the key things, that's easy to say it on this initial design, was the main structural components, this, and this piece here, they're all 4-inch by 8-inch quarter thick wall aluminum tubing. And the main change we made in the design from this to the final telescope was decided this arm didn't need to be this long, and after we built it, we actually cut it down. So I'll mention that. The base here was an existing equatorial wedge, one of the heavy duty guys, the guy that up at that worked for Boeing made, and we wanted to make sure that it would fit in my existing observatory. So the student did this drawing, and yeah, here's a better. And so these off-the-shelf flange bearings, quite inexpensive. I think they were like $40 each, 3-inch diameter, and the deck shaft was 1-inch diameter. You can see on this design, which changed later, the worm wheels are on the inside. Those got moved to the outside, and the worm assembly is actually donated by Kevin Iott at Plane Wave Instruments, and they're out of their A200 telescope. And so this is Luke Williams on the right. He's a student that did the drawings. He's analog devices, and he's up at he works at analog devices now. And this is Cameron Pace. He just got a job I guess a month ago at SpaceX down, and so he's moved down to Brownsville, Texas, and he's designing the machining for automating the welding and stuff on the Starship. At any rate, it's fun to work with a Cal Poly student. So here's Cameron, things being machined. So he welded up. That was a real pain in the rear, getting these welds on this thick aluminum. There you can see the motor assembly, and anyway, there's the various pieces, and here Cameron putting it together. We kind of test put it together in the shop. Another feature is the OTA had a regular dovetail that you could slide to balance it, but this gives you a rough balance in deck. Yeah, just unfasten this and change the settings of all these screws. It was in 1-inch increments. And there's the machine pieces back at my observatory put together. It's on a 10-inch, the inner pipe here is 10-inch. I think it's quarter or half-inch steel wall, goes down about a couple thousand pounds of concrete. So very, very sturdy. This whole telescope ended up being sturdy. One small thing I'd do different was it's a little hard to get your hand in this 4-inch space here. So a 6x8 would have been nicer to just to ease assembly, disassembly. there's Cheryl got it all put together with the instruments on the back end, kind of checking balance out and so forth. And so then had to start disassemble the whole thing, and got it powder coated, and there it is, reassembled. And note this photo here, this has a flip mirror eyepiece, and we eventually eliminated that. Didn't need the flip mirror. Never use this anymore, and so anyway, those really aren't needed. And here's the close up of the instrument cluster. So this is a Clement focuser, and it has a Pittman motor. And so it's actually two SciTech controllers. One controls RA and DEC, two SciTech 2 controllers, and the other one controls the focus motor. And we've got a third one that we may use for a flip mirror someday. But and then it's got a 5-position filter wheel. It was an 8-position. It didn't work. Dan says, send it to me. I'll see if it get working. And meanwhile, you can borrow my 5-position wheel. And he hasn't got it back yet, and he probably doesn't have the 8-position working yet, but I'm happy it's working fine. Thanks, Dan. And then this is a ZWO ASI 1600 camera, which has small pixels, but quite a few of them. And Dave Rowe, that's donated that to the project, and it's such we've added, you can't see it in this one, but we've added there's a little thing added in here with a 1.5x Barlow, and we're able to plate solve with it and do the Speckle. So it's a good, we can go down to 1 arc-second separation with good results. And I think this is the last slide. Last thing added, this was installing the high resolution encoder in RA. So this is sitting on the back end of the telescope. Here's the, you can actually see the telescope up there. And here's the worm drive as well. I was checking the run out before we took the tape off here to expose it. And this, on one of the earlier talks, on Dan's talk on the 32, and he talked a little bit about this device, which is really, really handy. So it's the read head, and you can just, I have a little Allen wrench I can turn, and it moves it in and out until you get the, if it isn't positioned right, you get a blinking red, and then a red, and then a green, and if you got it just right, it's blue. And we've been able to get a steady blue reading all the time. And so it's been a fun project, and I've enjoyed doing it. And so the initially a couple students used Nina and Sharp Cap to make the first set of Speckle observations, but we wanted that had no chance of being automated, and so Dan Gray had been working on ZWO cam, and that's what we've used ever since then. Dan's been very good about making changes, and Dan, if you can take it over from here, you can just share your screen, or if you need me, I actually have it going on the telescope out there if you want me to connect to the telescope and ZWO cam.
Hey, Russ. Well, I've got a little camera, but do you have is it dark down there yet?
No, it's not dark, so we
Yeah, okay. Well, then we'll just use mine then, I guess, for now.
Okay, good.
Let's see here. Which screen do I share? This one here, okay. So I didn't prepare much for this talk. So probably most of you haven't used SciTech EXE, but this is called the Sky View, and it's pretty nice, really simple, kind of a GUI. I wouldn't call it a planetarium program. That's why I call it Sky View, and it only shows this current sky. But what I want to show you is this software right here. And I'm connected to a camera. I'm just going to go over through some of the features real quick. Can you all see my screen?
Yes.
Okay, good. All right. So I'm just gonna, right now we have 0.001 seconds exposure time, so that's pretty short. A gain of 100, I'll change it to say 300 right now. And I'll just click continuous. And this one is not this camera is not a USB 3, it's a USB 2. And so it's coming in just pretty slow. But if I click anywhere on this screen, let's say there was a star where my mouse is. I hope you can all see my mouse.
Yeah, you can see it.
Okay. First I'll show you the configuration. So right now we have it configured for 256 by 256. So now we'll go back here. And as soon as I click, say right here, so there we have, we're coming in real fast now because it's 256 by 256. Right here, I have the time turned on so you can see the milliseconds for each part of the acquisition. What we found out right at the beginning is people got confused. What is going on here? So I put right on this window top, this name of the window, and it changes. It lets you know that you're in a region of interest. So then you have to right click to get it back out. So I'll right click. The other thing you can do is you can do a slice and surround by holding down the button and dragging an area. And then of course it's a little different. It's not 256 by 256. It's whatever you made it by your slice. Okay. Now, let's go through all of the tabs. Look at all the tabs that are up here. There's lots and lots of tabs. And I'm going to go back to I'm going to right click on that. So it's coming in. Once it's, let's just turn it off. Turn the continuous off. Okay. So focusing. So you can select your ASCOM focuser. I don't think I have my focuser connected right now, but any ASCOM focuser will work. So since I don't have one connected, I'll go with the simulator. We'll see if that works. And we'll say connect focuser. So it's connected. Now this is using Dave Rowe's autofocus routine from PlateSoft 2. He's saying there's better ways to do it now, but I'm still using the old way. So this is the exposure time right here. This is the binning. I usually use bin by 2, especially with the small pixels. And then I usually use 7. I think Dave has done 5, but I like 7. And then this is how many microns the focuser moves per step. And then you can do an autofocus, and you can see the focus position is changing. It does an image of this exposure, 5-second exposure. I should have done a shorter exposure for the demo. How many times have you used this, Russ?
Oh, it gets multiple times per night.
Yeah.
The focus changes fairly. The temperature here just drops like mad. We can have a 40-50 degree change over a few hours.
Okay, so now it's doing image 6, and we had asked for 7. So now it's doing 7. This is the last one. And then it's Dave Rowe's software is going to come up, and here it is. And it's analyzing each image. And it's not like not any one star, it's all of the stars in the image. And then there it is. Now, if you want, you can show the graph. And this one doesn't have much of a graph because there's no stars. Normally, there would be a nice kind of a parabolic graph, and it moves the focuser to the proper position for the best focus. And then now you're good until the temperature changes or whatever. Also, we are connected to the telescope right now. And if you look at SciTech EXE over here, this is SciTech. And you can see it's not communicating. I don't have anything connected up to it. But if you look at this right ascension, 7 hours, 10 minutes, declination 45. Is that minus 45 or 45? I need my glasses. Okay, I can look up better over here. Oh, it's minus 45. So this is using not ASCOM, but it's using my our TCP interface that is a lot faster and a lot more extensive than ASCOM. And you can like, for instance, you can do a sync. You can go to any right ascension declination or alt-as, or you can sync to it. So this is kind of complete telescope control right on this screen right here. And then this one here, I think it's used if you do the telescope. If you just click on this, do a photo offsetting net, it uses this information, and it uses plate solve 3 by Dave Rowe, and plate solves an image and will initialize the telescope automatically. Do you ever use that, Russ?
Yeah. So every time we move to a new star, we'll do the photo offset in it, and then it'll do it, and we'll often do a second one and move to it again to make sure that the double we want to observe comes right up on the X in the middle of the screen.
Yeah. So then it minimizes any error in, gears, models, time, all of that stuff. And then this is the plate solve. If you want, you can plate solve any image you want. You can browse to an image. Let's see if I can browse to one real quick.
Yeah, we also use the plate solve for the calibration inputs, the pixel scale and camera angle that we need for reducing the data.
Okay. So I didn't really plan too much of this. So this is kind of just, here's an M27 image. Let's take a look at that. Let's try to do a plate solve. Okay. Okay, so we'll click on telescope. It might work, but we just don't know. It's probably a much larger, oh, it did. Okay. So it's telling us a little warning. It's saying the starting field of view and position is off by more than 5 degrees. That's because we're not pointed at M27. So that's the little warning saying it might be a false plate solve. If you want, you can view, and this is the image that we just solved using Dave Rowe's plate solve 3. All right, so this one you can select a bunch of images. I don't have a bunch right here. I don't have this plan. This is a bunch of satellite images. We'll just select a few and just see what happens. I'll probably just stop this, but you can plate solve a whole bunch of them. You can actually update the world coordinate system in the FITS header if you want of a bunch of images. I'm not even going to do that right now. This one here is this one's, I spent a lot of time working on it and got it all working great. And then the people like Russ and then people using it found a bunch of bugs in it. And I think I got most of them fixed.
Yeah, we use it all the time now.
Okay. So you can load a sequence. Basically what I did is I looked at some other software and said, how do they do their sequencing? And I came up with all these options. And then how do you, do you have a button for every single thing? And I ended up just using like a kind of a, you just click and it figures out where you're clicking. And so then I don't have to have a million buttons. So this is line number 1. It's enabled. If there's a subframe enabled right now, then it would use that subframe. It's a light image. You can go to flat, dark. You just click on it and it changes. Exposure time, we'll just do 0.1 now. And then filter, you can select, this one cycles through your filters. If you want to go backwards, you hold down the control and it goes backwards. Bin by 2, gain, you can select your gain, let's say 200. And then how many exposures? So let's say you do, I'm going to do 10. And no, we're not going to add WCS because if you're doing like, a double star sequence, you're never going to do a plate solve. So I'm not even going to do that. This is, you can put a name for it and it makes a subdirectory name based on that. I'm not going to put one there. we're going to say workshop. And then we're going to say it's camera ID number 3. By the way, this software can connect to 4 cameras at once. And how you do that is you just run a different instance. Whenever you run an instance of this Cytec ZWO cam, it lists all 4 cameras, and if it's already in use, it won't use it, but you can click on one that's not used and it will start using it. And if you see this, if you see my mouse, see this is blue up here, and then this one's blue down here. That's how you can tell which image is which. So now we have a sequence, we have a path, and we can open the image path. Where did it? It's not opening. There it is. Okay. So we have a looms filter, and we already have an R subfolder, but we're not going to use that. We're just going to take 10 images, and it should make it a subfolder called looms. Let's just see what happens. So we'll just say start sequence. Okay, there it goes. Okay, it made the looms folder, and let's take a look. See, there they are. We can view any one of them, and there's a hot pixel. There's nothing there. Again, this is Rowe software, PlateSolve 3.65. I generally use it just as a viewer as well because it works so well. You can add a sequence line, and as soon as you add a line, it adds an identical line, and then you can change it. You can change the filter or whatever, and then you can make a loop, and it'll just loop that many times. It'll do every line and then loop. So if I add a loop of say 2, and then now it loops through it. So this would make 30 exposures, because the first time through, then it does the second time through, then it does the third time through, because there's 2 loops. So that would make 30 exposures. But you could also change that, and it makes a separate folder for each filter. Scripting, this isn't done yet. This is what's going to be controlling the roof and all that stuff. Configuration, we have a lot of configuration items. So you want to set up your camera field of view so that the PlateSolve works properly. And then you can also put the camera angle relative to the parallactic angle 0 if north isn't up. And then your site information. If you do have Cytec EXE connected, it'll get it from the telescope or Cytec EXE. So a lot of this is done for Vishnu Reddy at the University of Arizona, and a lot of his stuff is done with just cameras mounted on stationary cameras, on stationary mounts. And so he wanted to, he wasn't connected to a telescope, so he wanted to be able to calculate the latitude, longitude, and the right ascension and hour angle and declination based on, and so that's what this configuration is for. You can set up your filter names, and this is remember when I can go ahead and click, let's bin by 3 or 4, do continuous, and then if I click on 64 by 64, so now it's going to be a real grainy picture. There, see? If I click by 512 by 512, so I right click and then left click again. So, you can see the difference. It's always the same size of image. It just scales the pixels. So that's what that does. You can change the brightness, and you can you can do linear. If I do linear, I move the brightness up, or if you square root the image, then it's a little more stretched. Configuration 2, this is this uses a TCP, so you can actually run this on a different computer than Cytec EXE, and you put the IP address of the computer that's running the telescope, and then you put the port number, and then you have to put your port number if you want other instances to access this. Like for instance, Dave Rowe is able to access this software and make a sequence of images, and he needs to know this number right there. This is something that Vishnu Reddy needed to, so if you start a sequence, it starts it on 4 different cameras. Here's a few Boolean. If I draw the path, that's the path of the right ascension. You can draw crosshairs on it. It'll actually find stars. And then there's some work in progress about guiding and tracking satellites. There's a bunch of messages, a little kind of a console that tells what's going on if there's any problems. And that's the software in a nutshell.
Okay. Dave Rowe, can you hear us now? Can we hear you?
Can you hear me?
Yes, yes.
Yeah, I had to switch to an old laptop.
Okay, well, I'm really gratified you were able to get connected here. I got your email and my heart just sank. So, okay, I guess you're up now. It's your turn.
Yeah, it's nice to be here with y'all. I'm sorry I couldn't make it for the last couple of sessions. I had family here with me. So I'm on an old laptop and I don't have a new software, so I can't actually share my screen and show you anything interesting, but I can try to describe it in words. The idea is to do an automatic acquisition of a list of double stars, and that list comes from a computer comma separated variable file, something that you can output from Excel. And my program reads the file and parses it and automatically will then run through that list of double stars. And along with the list of double stars comes a list of filters that you can apply to that acquisition and so forth. So I'm in the middle of writing that. There's quite a lot of interesting.
Oh,
Is that me?
I can't tell. I don't know.
Okay, so okay, so the things that are, the interesting thing is the things that are necessary to do to make that happen. Each double requires a reference star. So I'm using the SAO catalog and finding the nearest one that lives within a certain magnitude range and a certain distance away from the double and so forth. We have to plate solve we don't have to, but I want to plate solve the image to make life much easier. If you don't plate solve the image, then you've got to do what's called a drift calibration of your camera. And drift calibration is not so bad if you have an equatorial because it doesn't change very rapidly. But I want to do this on alt-azimuths like a plane wave 1 meter that we're going to have operational in Chile pretty soon. And then the problem is really difficult because there's a rotator rotating and there's a lot of opportunity for small errors to creep in. So it's necessary to plate solve these images for that reason. We have to automatically set exposure times. We have to automatically focus. Automatic focusing is a bit tricky, and so forth. So there's quite a lot of tactical stuff. The strategy is pretty straightforward, right? You go to a double, you go to a reference star, you take a bunch of images, you store them in the folder in an appropriate folder, and then you want to kick off the processing, after you've on another thread, after you've taken the images. The strategy is really simple, but there's a lot of stuff in the way of that. So I'm in the middle of working with Russ on that. I'm using Fyro, and we'll proceed until we make it work. I'm using Dan's software that does the actual camera control, which you just heard about. And he's written a TCP interface for me that's simple and adequate for the task involved. Something that you may be interested in is in the 1 meter in Chile. We're going to outfit that telescope. It's a partnership telescope. There'll be 4 partners. PlaneWave will have 1/4 of the time. And we'll have port number 2 kind of to ourselves. So on port number 2, we're going to put a Botter optical switch, which then allows us to have 3 different instruments on that same port. And those 3 instruments will be a Speckle camera. We'll use the ASI 6200, which is the full frame, what is it? 6200, 62 megapixel camera. And we'll also have a spectrograph on one of the ports, and then on the big through port, we'll eventually have an SCMOS large format imager. And that telescope is it's within seeing distance of LSST and GMT and so forth. So it's on that mountain. I've never been there, but it's on that mountain. And we get 1/4 of the time, but nobody wants to use bright moon time. So we'll actually have a lot more than 1/4, because we'll probably take most of the bright moon time. It turns out that Speckle is very insensitive to background because you're at such a high magnification. And that means that each pixel is receiving very few photons from the sky background. So you can live with it. It doesn't degrade the noise very much. In fact, not really at all until you get to like 12 meg per square arc second or something like that. In other words, even a full moon isn't going to have much of an impact on the noise in the acquisition. So we're very excited about that. That's happening in the next few months. I'm about to order the equipment for doing Speckle. We already have the spectrograph. We have the optical switch courtesy of Botter. He's a great guy, and he's given us an optical switch. So we're going to buy the rest of the stuff and get it down there pretty soon. The telescope is finished. It's on the floor being tested. And it'll be crated up, I think, probably within the next month. So we'll have that pretty soon, and we'll have it for students. The students will be able to do it manually, because it's got to be fun to operate a 1 meter telescope, right? But then we'll have this automatic acquisition program. And I didn't catch Russ's part of this, sorry. I had a Windows 10 update last night, and every microphone that I have has disappeared. Nothing now works. I suppose it's some setting that I can't find in Windows 10. But so I was fooling around with that, and I wasn't, able to listen. But Russ has some nice programs that we research, really good science research programs. And of course, Rachel and Calais and others have students that are, interested in this and will write papers. And it's really a beautiful program, I think, for everybody. Okay. Thank you for your attention. That's basically all I had to say, unless you have questions.
Well, we have a question from Akers who had to leave, but he wrote in the chat that he had a question about what is the key feature that you guys are looking for that Nina or K-Stars, et cetera, doesn't offer.
I don't, Russ, take the question, please. Unmute your microphone.
Okay, I just answered it via a chat.
Oh, yeah, I just see a pop-up now.
Yeah. One of the key features is you can access it using a TCP interface. For instance, Dave has just mentioned that he can request a sequence of images and put them wherever, you know, using this filter, this exposure time, this gain, and put them here. And so that's probably the biggest key feature. Plus, it's pretty simple and it's all in one. It controls pretty much everything. So
Yeah, the all-in-one feature turned out to be really important. Switching between a bunch of different programs is a pain. Plus, we were really interested in heading in a direction towards full automation.
Anyone else? Okay, well, Dan, why don't you take your quick 5 minutes here to update us about the breakthrough you had for Jimmy's 36-inch based on comments you received on Thursday.
okay, can you guys hear me?
Yeah.
Okay, I got to figure out how to share my screen. I'm pretty slow at this. Share screen. Okay, you're always going to see a double image. Okay, here we are. Oh, that's programmed. Okay, minimize. All right, so this is all done with FreeCAD. Let's see if this is it. Let's see. Okay, so I've known this for many, many years, that you don't have to make a circle to make a motor. You can make a linear motor with, or you can make an arc of a motor and it'll work just fine. But I forgot about that. And then Rob Brown made a comment about, and I had a problem on this design. I had to figure out how to support the magnetics way up high, way higher than the axis of the altitude axis. And he said, well, why didn't you do that? So I made because of what he said, I made an arc. So let's start turning on some of this stuff. Okay, so this is the fork here. Dave, you didn't see the whole model of the other telescope that I gave on Thursday night. But so then I made this. This was on Saturday. I pretty much designed this, or Friday and Saturday. And so since I wanted to not have anything up here where my mouse is, flapping in the wind, so to speak, I wanted it all to be solidly to the fork. And so I instead of doing that, I made a dual motor. So these blue things here that you can see are coils, and then these are the magnets. So it's a dual motor. So it's about 9 coils instead of, I think, 24. So it's not 180, but this will turn 180. That's what these sections of the magnets are for. So you can turn the full 90 degrees that an alt-az telescope needs to move. But it's all down here and all backed up by solid structure. And so that was a really good thing. Thanks, Dave, or thanks, Rob. Are you here, Rob? Rob's not here tonight. Okay. So then on Sunday, no, this would have been Saturday, I got a call from Joe. Are you here, Joe? Joe LaCour? Yeah, Joe's here. I see him.
I'm here.
Okay. And he said, well, why don't you put the magnets all and the coils underneath the mirror for the altitude? And, you know, well, that has a huge advantage. First of all, leverage, and then second of all, you can put it in the center so it doesn't try to twist the frame. And twisting is a huge thing. So if the structure twists, and I have some experience with that, it's really hard to control. You need to use a notch filter, and even then it's just a mess. And so that was one of my worries. I didn't want to do that because, you know, that's, you got to make it taller, and you got to have all these big coils of, you know, so, but he got to me thinking, and it wasn't until this morning I thought of this. So he gave me the idea. Instead of, I went back to a 1-layer motor. So there's the coils, and then there's the magnets, but I put one on each fork. Now the advantage of that is you put a torque on one motor, you're also applying it to the other motor at the same time. I mean, instantly. And so there could be a little flex in the mass of the mirror and so forth of lag, but it's going to be way better than if you're trying to just twist with one motor on one side. And so I'm just going to do it. It's going to be so much better. And it, you know, like I said the other night, I said, I get paid to worry. And just like Dave Rowe says, he says he gets paid to worry. And, you know, I feel the same way. And this is one big worry off my mind. And it's because of this workshop here and some comments that we got. So that's it for me. I just wanted to show that off.
That's really cool. That's really cool. That's the kind of thing that makes this feel like a workshop.
Yeah.
Okay. Ed Allen, are you out there?
I'm here, Howard.
Okay, Ed, you're up. Updated clutch system.
Okay, do I have the screen?
Oh, before you get started, can you sit up a little bit so we can all see your T-shirt?
Oh.
Yeah, I like that.
Okay, let's see. Okay, there we go. And let's see, do a screen share. And we'll start here. Okay. All righty. So, Howard, I think what I'm going to do, kind of keep it light tonight. I'm going to start with some very basic stuff and kind of show everyone a few alternatives to the more elaborate electromechanical or electronic clutch systems, because I think there's a big opportunity out there for everyone to maybe rethink a little bit what we're doing with the motion on these on the manual scopes too, as well as the tracking and the go-to versions. So I just wanted to kind of go through some have to move this here because I can't see my stuff. Go through some basics, if you don't mind, if you'll just bear with me. Did a little bit of a thinking about this, and we have the single state systems, which we're familiar with, that was popularized by John Dobson. And they're technically really a sort of a two-state system. We have the states of static and kinetic friction on either side of a threshold, but they don't change physically. So I think of them as a single state system. And they're pretty much based on fixed material properties. Everybody knows them, ebony, star, nylon, et cetera. And they're also dependent on area and pressure. Some of the very good things about them, they're simple to build, they're inexpensive, they're dependable. There's a large knowledge base online, and there's no power requirement. But they do have some problems. For me, the two biggest ones are listed here, and that is they have a contaminant, moisture, temperature, wear sensitivity. And for me, this translates into consistency. I like a scope that works identically at 85 degrees or 20 degrees, and I like it to work the same year after year. I don't like to have a different feel to the scope. I like for it to stay very, very consistent. And the single state system relies on this separation between basically two states again, of the kinetic and static friction. And I've kind of indicated here some of the terms that we might use when we're discussing it: stiction versus friction, locked versus unlocked, and tracking versus push to. These are kind of some of the terms that we might think of this system. And the one thing that it has in common across all of them, whether it's John Dobson or say a slipstream system with a push-through clutch, and is they have a threshold. And on either side of the threshold, you have these two functions. There's a very limited amount of distance between those functions because of the properties. So moving on, when we move into the idea of a multiple or variable or two-state clutch system, they can be subdivided into all mechanical and electromechanical versions. And these combine mechanical properties along with any material properties that we so want to get the end result we desire. The negatives primarily are increased complexity. They're a little bit more expensive, but I will show you a low-cost version here in a minute. And the electromechanical or electronic versions require power to function. The good news there is the normal power supplies we put in telescopes work just fine for this. One of the advantages of going to a multi-state system is that we can make them very contaminant, moisture, temperature, and wear resistant for that consistency over time. I would expect for a scope to act the same for years, whether it's exposed to, say, OSP or in my case with 2 foot of snow outside right now, work exactly the same way. So the idea is that we want to increase the gap between the two functions. One function being a free float that we have down here, the other one being a more of a rigid position or state that we want to stay in. And we want to make that gap wide. And I've learned through all my testing and 4 years with this system and all the earlier experiments that there's a little bit of a misgiving out there in that you don't want a scope that can be too free floating. I have found that not to be the case whatsoever, especially on all manual telescopes. The more free floating it is, the easier it is to operate, the easier it is to point, and such things like overshoot were not an issue whatsoever. And that was basically the impetus for this. So increasing that gap has freed up a lot of things, and I'll show you a little bit how it kind of impacts use by an observer. But one of the best things is that without the stiction threshold, the push-to force movement is naturally proportional. You push an ounce, you get a little bit of movement. You push 5 ounces, you get more movement, more distance. It's very proportional in all directions because you're not crossing a threshold between the two states. So this is some of the user impacts. And sort of like Mel's situation with a 3-axis bearing system, this is another solution to Dobson's hole. And it makes maneuvering in that region extraordinarily easy, pinky finger easy. And it's particularly useful for larger scopes when operating from a ladder where you have limited leverage. So it is possible to have a jumbo scope, be able to move it with a finger and yet have it stay in place so that you don't have to worry about things like wind and whatnot. The next thing down is I got a show here is the star hoppers and large object observing dream. It's great to be able to move the scope around and float. These ultra-fast telescopes have this wonderful ability to soak in large chunks of the sky, and when you combine that with free-floating capacity, it adds to the experience. You know, you can follow large extended objects, trace things around the border. If I want to go to like North American and trace the border, it's really, really easy. And there's no thresholds, so the proportional movement is finer. The next thing is the multi-vector movement is significantly enhanced. In other words, you can go through circular searches and whatnot. It's very, very easy. The clutch can be designed so it can hold your scope in the wind, gives you a little more expanded opportunities, makes it bump resistant, which also means that it's fiddle resistant when you're focusing and whatnot. You don't have to worry about it moving around. One of the big things that I really like is that it securely holds the position of the scope when you're changing eyepieces or focuser loads. I'll show you that in a little bit. And there's no balancing required. As long as your scope's balanced pretty much in the middle between your load range of the lightest to the heaviest eyepieces. Like, for instance, my case, I might go from a little planetary or something up to something like this, a big night vision stack with a big eyepiece. I don't have to rebalance the scope. The hand on the handle is naturally compensates for the imbalance, because when it's loose or free floating, your hand-mind handle interface is just automatic. You don't think about it. You put it where you want it, and that's it. Another major thing is that it minimizes the torquing of the structure when you're moving it. If you're pushing against friction, you're going to torque the structure a little bit. And it means that when you release, there's going to be a little bit of rebound. You're going to have a little movement in the eyepiece. And that's another thing that you pretty much eliminate when you go this route. Another thing that's helpful for me is it holds the mirror box at any angle during assembly and transportation. When I'm putting the cage on top of the scope, I'll usually drop it over about 60 degrees or so, engage the clutch. It holds it there in place for me while I'm adding and removing the cage, so I don't have to hold it up so high. So those are all common elements that are parts of both mechanical and electromechanicals. And then we have a few more things we can do with the electromechanical over just a pure mechanical. It can provide improvements in tracking and go-to. And I found this to be very true because there's a good solid connection. There's absolutely no slippage of the drives. It indirectly allows for some improvements to backlash. I can show you that a little bit later. And it helped me here recently with the improvements to the free float mode of the scope I did over this last winter. I was able to reduce the backlash to roughly 1/10 of what it was before. It also allows a number of expanded opportunities or capabilities for protecting the drive system, for instance. In this case, you can set the maximum torque to protect the drive. On this scope here, I've got it set for about 25 pounds in each direction. So 25 pounds in either direction of alt and 25 pounds in either direction of altitude. That's what it takes to move the scope off target. If I push 25 pounds on here, see, I've got it locked right now. So if I put 25 pounds of torque on here, I can push it off the target, but whenever I let go from the basically just super stretching of the timing belt and what little torque I can do on this frame, whatever I'm looking at on the crosshair and the eyepiece will drop right back in the center. So it's wonderful because you can start with a low power eyepiece and start ramping up, ladder up. I do that all the time to kind of test seeing conditions. And I know without any doubt that whatever I have it on will be in the eyepiece as I'm removing eyepieces, adding them, slamming them in and out, in and out. It just doesn't make any difference. The last item is something I've just contemplated about, and that is I've set this scope up to about 50 pounds of torque for movement in the altitude. So on a very large scope, it would, with a good bearing and gear system, It could be that this would be very good for a really large jumbo ladder scope, in that if somebody was to lose their balance, all they have to do is grab the scope and write it down slowly. So it could in theory act as a safety, or as a means of at least holding on and rebalancing yourself against the scope while you're on top of a ladder. Okay, for the two-state all mechanical brake systems, I call them brakes because they're all mechanical, and there's really only two states, free float and a brake. There's no power requirement. That's pretty obvious. And just as before, anytime that we can minimize the alt-az bearing resistance, it improves the multi-vector free float maneuverability and positioning. It also allows a redesign of scopes in that the alt bearing does not need to be these large assemblies that we have. As a matter of fact, it could be as simple as, let's see here. You can just have a bearing on a shaft, bearings, bilge blocks, whatever. But we don't have to have these large alt bearings with the system, because we're shooting for minimal resistance, which can be done easily with just two standard sealed bearings. You can do a friction adding adjustment if you wish. I find it's not necessary. Some folks might want to add a little bit for some sort of feel, but I found that that's not necessary. And I'll show you a little later that I actually went back and removed all the friction adjustments that I could add to the system. Anytime we can do one step removed or dual-sided braking, it'll further minimize image shake. That just simply means not pressing necessarily against the an alt bearing or azimuth plate or something like that. We obviously have to have an ergonomic consideration of the lever that we're going to use and its placement. That's very important. And this next to last item is very important also, in that high power observing requires feathering of the hand release. In other words, we want to have a brake that we can gradually release the handle, so that, or just feather it at the very end so that it doesn't jerk on us and things like that. Then of course you always have an option to lock it in. So this is very simple stuff, guys. I know this is 101, but I just kind of wanted to show you how easy it can be to do on a scope like, say, Mel's 25. This is about $20 worth of stuff, built from inexpensive bicycle brake kits. You start off with a handle, with a trigger, a simple bicycle brake cable that's spring loaded. We have a couple of friction pads. Excuse me. Different ways of doing it here. It can all be quick connect, so you can disassemble your scope. The trigger handle would probably be on a cage if you have a truss, and it would be on the top of a tube if you have a tube. I'm getting some noise.
Rob, is that you making all that noise? Okay, I think it's gone now.
Okay, very good. So anyway, bicycle brake assembly for the vast majority of these, all these manual knobs that we have out there would work extremely well. And I did experiments early on, use something like this to figure out some of the basics of how this is all going to kind of work out. I eventually went to electronic, but this does work well. And everything you need is basically built in. It just has to be reconfigured a little bit. It's not too hard to do in a very light machine shop. And the parts that come with it, for instance, there's fine tuning of the position of the pads with little knobs to lock the position of or little nuts to lock the position. So you can basically pick up everything you need. I think $20 was what I saw just today for a 2-meter kit, which is two 2-meter cables inside of a little plastic sleeve, some handles, a couple of brake pads, a couple of calipers, a couple of springs, and all the miscellaneous hardware. Not expensive to do, and it can be applied to a lot of different all manual jobs. So here's just a picture of one of those kits. And like this one here is another picture of a kit. This can be salvaged and used inside of a tube to make a nice little handle. You got the cables, brake pads. These are basically a friction pad, and caliper, pivot point, springs. Okay. Here's another sample if you want to go super light, because other kit weighed about a pound. So a pound for a whole scope. So here's another version. I think I got this at a model railroad store a couple of years back. But anyway, it's as you can see, it's only 7/100ths of an inch in diameter. And I'll just show you how it works here. So it's very simple. Okay. This is a stainless steel wire or rod. It's a spring steel stainless inside of a Teflon tube. So that would work for the smaller scopes and be very easy to install. This don't rail on me too much here, guys, because I just threw this together. This is definitely a super simplified thing, but I just wanted to show you a little bit how things change when you reduce or eliminate the friction down to the point of where it's almost not there. Things change when you move the scope around. You don't have the problem of a threshold. And in the case of a diagonal movement, you have two thresholds you have to break, in essence. And you also have fixed friction in both axes, and you have less leverage in both axes when you move a diagonal. That's why when I've observed a lot of folks using their manual jobs, they tend to stair step. They either go left, right, or the up and down. They don't do as many diagonal movements because it's just a little harder to do. Okay, so now let's move on to the electromechanicals. Requires power. I think that's pretty obvious. One thing I found works very well is to use reciprocating mechanisms, and especially using a momentary pulse power, which reduces the power use. In this case behind me, it's about 1 amp for about 0.2 of a second or less is the power required to change from state to state, from one to the other, and nothing is used in between. And it has the same ability to improve the multi-effector. We talked about a couple of these things. Let me just move right on down here. There is a difference on the high power observing. From the handle, no matter what kind of switching you use on the handle, the low power and mid power works just fine with that. But at high power observing, which I kind of put into in my case, about 500 up, then you need to start thinking about physical decoupling of the engaged disengaged switch. It's not because of a limitation of the electronics or the handle or the sensor or anything like that. It just has to do with our hand. And that if we make a scope that sensitive, when we're releasing it, the padding on our hand or a glove can push the scope a tiny bit. So we want to overcome that. And the best way I've found to do it so far is just simply remote that switch into a very convenient location that doesn't, is not on the cage, but it also doesn't rely on keeping the hand around a handle. So basic electromechanical clutch system, there's not much to it. Power source, some sort of reversing circuit, self-latching reciprocating devices like linear actuators. There's different ways of doing it, particularly with built-in limit devices can shortcut the whole process, make it easier, but the circuit's very straightforward. Here's a sample of a linear actuator. It's not much to it, just a power pair going in. It's polarized. You apply power to it one way, it pulls in, you apply power the other way and it pulls out. That's it. So this is the scope behind me here. And I'm going to zoom in on the linear actuator and some of the clutch. And by the way, Dan, are you listening?
Yes, I am.
Yes. Okay, so right here, I'll show you this. If I get back here a little bit. I don't know if you can see this. This here is a screw jack drive, and I salvaged that out of that came out of a Ford Rangers. And I just chopped it down. It's nothing more than a Acme drive that's telescoping. And so that whole assembly is about 4 inches high, but it extends an additional 6.5 inches beyond what you see there. So that drive, this motor, very simple. It looks like a kludge here, so I wouldn't necessarily recommend this exactly, but the idea is that a screw drive like this can lift about 1,000 pounds or more. So in Jim's scope, that might be something you can think about. The power requirement is about 1.25 amps at 12 volts to lift this scope, which is 305 pounds. So it's very efficient power-wise. And in this case, the screw jack works because there are anti-rotation sleeves, free-floating anti-rotation sleeves that travel with the foot plate. And the foot plate's about 5.5 inches in diameter. It's a semi-sealed system. In other words, the screw jacks are not exposed because of the traveling sleeves, anti-rotation sleeves. It makes a very, very simple, modular, compact way of lifting a very heavy scope. I tried other versions. I tried a chain going around the outside perimeter. The power requirement was tremendous. I would have had to have a huge battery system to operate it. But this is many times more efficient because basically we're driving, the screw jack just goes up through here through a bevel gear and just drives straight down on axis. Okay, so anyway, sorry guys, just jumped off there. This is a linear actuator here. And it's inside of a rubber jacket. And that's just for extra moisture and noise control. The linear actuator in this case has built-in limit switches, which are set outside the range I normally use. I kind of ignore them, just use them as safeties, and instead added high MTBF snap switches to the outside that can be easily adjusted. So these can be moved around real easy, where the ones inside would require disassembly of the structures or the linear actuator to actually get inside them. But they do the same thing. They're steering diodes or reversing diodes, if you want to call them, there. And what happens is this moves back and forth less than 1/4 inch when we activate the handle. That moves this lever arm here, across here. This is a pivot point. So a little less than 1/4 inch movement here gives us about 1/20 of an inch or so movement out here on this yoke. A yoke is a really easy way to do it. The yoke presses against the transfer assembly here. We have a hub and some of the rest of the unit. And I'll show you that exploded in just a second. But I wanted to show you how it looks in the azimuth drive, so you can get a little better sense of how it's all laid out here. The rest of this is pretty standard stuff. We have a reduction worm. This is a ultra low backlash worm. And then of course it's driven by your multi-beam coupler, and then into the Pitman reducer. I think it's about 10-to-1, and then the Pitman motor on that. So let me just drop out of here. And Dan, there's your little unit there. You probably recognize it.
Yeah, I've seen one or two of those.
Yeah. Okay, let's see. Okay, here it is in the altitude drive. Same thing. We have a linear actuator back here. Here's the lever arm. We have some high count or high MTBF switches. I think these were rated at 15 million operations these switches, plus or minus 15 million. And again, the same drive system. Looks very similar to Howard's because that's where I got the idea from. Let's see here. Okay, here's the clutch exploded. And what we're doing here is we have, this is a part of the redesign. We have a yoke. We have this simple cover cut made out of Delrin. I have to confess, I just obtained my first lathe this past winter. So I actually built this scope without a lathe or a mill. And so I've been learning how to use it, self-teaching. And so this is the assembly that I've come up with. We have some thrust bearings. We have a timing belt hub. And one of the new improvements now is inside the timing belt hub, there is a roller bearing assembly, a precision roller bearing assembly. And so this hub spins on this 1-inch stainless steel shaft very, very easily. There's almost very little friction. You just spin it and it just goes quite a while. Bonded to the hub here is a brake or clutch material that you can buy in sheets. It's bonded with a combination of a 3M, I think it's called 1800 adhesive, which is a cross-bonded adhesive. It requires heating it to about 400 degrees for an hour under pressure. It's the same stuff they use more or less for bonding brake shoes and clutch plates to metal. This is actually easily done. In this case, all I did was pass a bolt through it, put some washers on either side to apply the pressure. And when I took part of this, some parts down to the powder coater, he placed them in his powder coat oven for a run when he was doing everything else. So it made it very easy. On the opposite side, again, more another thrust bearings and thrust washers. We have some spring waffle style spring washers here that force separation. At the end, we have another clutch ring, pressure ring here. And then on that, that's been bonded to a standard shaft clamp. Okay, and put together, it looks like this when it's all compressed together. That's it. That's the entire assembly. Okay.
Awesome.
This here is, I'm going to skip here just a little bit. This is one of the changes I made because of the reduced friction. I was able to go back and rework the what I call friction drives. It means just like Howard's, these shafts drive the altitude bearing, and also in the case of the azimuth, there are wheels that drive the bottom side of the rocker. So it's a friction drive, but in this case, I reduced the diameter of the collars. This is what the trunnion actually runs on, down to this. And this clamps or slips over the 1-inch shafts that the scope rests on. So now I'm at a ratio of approximately 26:1 on the final friction drive. And I was able to do that because of all the other friction reductions because of the clutch. This was before. I have 3 of these before supporting the azimuth. This it had a 1-inch drive shaft and these 3 3/4-inch Lovejoy wheels. That's been reduced to now about 3/4 of an inch with a single 1-to-1 transfer bearing to get us up to the same dry point up here. And so again, now the azimuth is, instead of roughly 4:1 ratio, it's 26:1, the same as altitude. And that was a big help with the reducing the backlash. And so here's the backlash afterwards. I don't know if this is good or bad or whatever, but this is what I'm at this point. About 1/3 of an arc minute, I guess, or below. For a larger job, I don't think it's too bad. Dan, what do you think?
Yeah, for a visual scope, that's going to be definitely acceptable, especially since the tracking is always in one direction.
Right, right. It's always loaded one way or another. Okay. Okay, let me just skip forward here. Let's see if I have any more. No, I don't. I'm going to go here behind me and show you how this works. But I tell you what to do. I just want to go back a little bit. So this is a schematic for the scope, and just wanted to show you here, we have a linear actuator. It's nothing more than a DC gear motor with a little different configuration. We have a couple of external switches. We have a couple of steering diodes or reversing diodes, and they go up and they're driven by a single channel on the H bridge, which is, let's see here. That's one of these little guys, okay? Less than 20 bucks. So that's a little H bridge circuit. This is a dual circuit, and I'm only using one circuit to drive both axes. So both altitude and azimuth are just using one of these. And there's two of these in the scope. That's 4 channels. So 3 channels are used for the legs, for the screw jack legs, and 1 channel for the clutch. So anyway, I just wanted to show you that. Okay, so let's just go out of screen sharing real quick. Gotta move this. All right, can everybody see me?
Yeah.
Okay, all right, I'm gonna go to full screen here. So I wanted to just kind of show you how this works. We'll turn the scope on. First of all, right now I have it in push to mode. So all I'm going to do is just put my hand on the handle, and you can see the scope how it moves here. Okay, and the handle set at an angle, very comfortable for pointing. The ergonomic considerations need to be made, obviously. In this case, I did use a capacitive sensor. I've tried a couple, including an infrared. The capacitor sensing is on the back side. It's long, kind of long oval shape, and it's about a 1/16 inch off the surface. So I don't actually have to touch the back of the handle to operate it. And this is really, really good for all low power observing and almost all the mid power observing. It's all you need. But at high power observing, again, you get that little rebound off the hand. So what I've done is here, I've added a little button on the side of the console, if you can see that. So when you're doing your aiming, you get exactly where you want it. I'll change the mode here so the handle doesn't work. And you put your object where you want it, and you just tap the button. And that locks it in right on target. 900X with a crosshair is not a problem. So the next thing I want to show you is, let's tell you what I'll do here. I'm going to go to this mode. All right, and here and here. Okay, now I'm in free float so that I can show you how the scope kind of now works. I want to first go in rotation on the azimuth. Okay. Okay. See how that works? Just very little force is required. It's very, very low. And you see there's also some coast. Okay. And as far as the altitude is concerned, do that for you. You see how that works with the altitude. Okay, so now when you're doing circular searches, you have almost no resistance. Just float it around. When you're working zenith, you just float it around. There's almost no resistance there. Okay. And of course, once you go electronic, you can add other functions, like I can defeat the handle so that so that it doesn't work. If I was doing some outreach or something, that'd be obviously a way to keep people from playing with it. But anyway, that's how the scope operates. And then if I wanted to disassemble it, go here. If I was going to disassemble it, I would put it like somewhere in here. Let me do this here. Sorry about that. Don't know how to do it. So unlock it, lock the scope in position, and now I can remove the cage without being so high. Okay. And I guess that's most of it. Let me see if I have anything else in my notes. Oh, there is one other version out there that you can do, and that is a hybrid. A hybrid would be electronic, you have tracking and or go to, and you can use a mechanical clutch to do the clutching of the system, just like I showed you before. And instead of moving brake pads, you're moving yokes on your power transmission. So that's a third way of doing it. Okay, that's it.
Well, I need to wipe the drool off my chin. That's that's really awesome, I have to say. When I used it a few times at OSP last year, like I mentioned, it was just so fun to grab that handle and move the scope so effortlessly, and then let go and have the scope just lock itself in. That was really awesome. All right, any questions out there?
Yeah, and this is going to be a super basic one, but so in a purely mechanical mode, the suggestion here is that unlike doing the traditional Dobson stiction thing, that the bearings and whatnot would be as low friction as possible to allow the easy movement, and then rely on the clutch to basically lock it in position as opposed to the stiction. That's the basic manual premise here, right?
Yes, it is. And I didn't miss one. Whoop. Get back to my screen here. Come on back. Hey, did I lose you guys?
No.
We can see you.
Okay. There we go. Very good. Okay, it's the chat that's in my way. I'm going to go back to screen share just a second and show you one little thing I missed, but it's very important. See if I can get this to come up. Yes. Down here, I have a little note called nudgers. All right. When you're doing a manual scope or a manual Dob, you have to be able to move it to keep up with rotation. So what you can do in this time design is simply move what's on the left here. Move this point into the nudger category. You don't move this on the right. You keep this where it's at, and you just move this over to the nudger so that you have just enough friction to hold your positions and everything, and then be able to nudge it. But you don't obviously want to lock it too hard because you can't nudge it. So, instead of having this little tiny gap here, we still have a gap from here all the way out here for the difference in operation. So it can be fine-tuned very easily for the nudgers in an all manual design.
Mm-hmm.
At least that's what I call them.
Yeah,
I don't know what the official name is.
Yeah, well, it's nudgers now, I think.
Yeah.
That's really great.
Ed, this is Rob Brown. Can you, is there any way that we can see your handle up close? Or are there any buttons on your handle? I'm kind of missing something here.
Sure. Let me pull this up here. Okay.
Yes.
Okay. Can you see me?
Yeah.
Okay. Okay. I got to get there. Here's my screen. Okay. So let's see here. There we go.
Oh,
okay.
yeah.
So here's the handle. This is just off of a hammer drill. Okay. A burned out hammer drill. This button here is for the targeting laser. Okay. So when you're moving your scope around, you can just press on this and it fires the laser, right? And so that's all that does. The capacitance sensing is roughly a 1/2 inch by 2.5 inch rectangular area on the back here. And it's set about a little over 1/16 inch out, so that if I have heavy gloves on or something, it still works 100% of the time. Yeah, that's just the handle. I don't know.
Do I hear the actuators moving?
Yes, you do. Just a little bit of noise there. Yes, just a little pulse.
Awesome. Thank you.
And we didn't talk about the collimation. That'll be, I guess, another.
That'll be another one. Yes. Yeah, we could do a whole workshop on your telescope, Ed, feature by feature.
So you have a permanent green laser mounted in it as well? That's what that button does?
Yes. Let's see here. That is, let's see, make sure I have a safety lock down here on the console to make sure nobody's using it, but there it is. And it's coming out of the tail rad. So this button is can go both ways. In other words, you can press it in all the way, it latches, or you can just press it in with your thumb. It just triggers momentarily. Does that make sense?
Totally.
Yeah, everybody has a green laser inside their tail rad, right?
Oh, sure. Yeah, like I said, we could do a whole workshop on your telescope. There's so many great features. Oh my gosh, hey, more questions out there?
Am I going to have to upgrade Quinsight now?
It's up to you. Could be an opportunity.
Yeah, and I would love to see that. You know, the Quinsight, if it had a user replaceable reticle, particularly with NCP, and because of its wide angle, it'd be great if it had some of the stars around, Polaris included. Then it would be a wonderful addition for the SciTech to be able just to do a quick NCP alignment, because your Quinsight does do the rotation. That'd be kind of nice.
Cool idea.
That's a good idea. I'll think about that.
And the 4 or the 3 jack lifts or whatever, is that just for leveling?
Yes, the scope has auto level on it. It's accurate to within about 1/100th of a degree. Yeah.
Auto leveling. Wow.
Yeah, like I said,
which I would definitely put on Jim's scope.
Oh yeah, well that's yeah. I think we should probably wrap it there, because like I said, we could do a whole workshop on your telescope. There's so many great features. We'll save some for next time. So the final presentation has been recorded on a video. I mentioned it at the beginning. This next generation telescope program at TNO, and it is kind of a treat for those of us, especially who've been in the Altaz workshop from the beginning or near the beginning, as we were looking at the large professional telescopes for our inspiration. So this is I think perhaps the first instance where the professionals look to what one of our members was doing as inspiration. So without further ado, I'm going to try to get this video going so we can all see. And let's make that full screen. And here we go. Can everyone hear the audio?
No.
No, not at all.
No audio.
No. No, neither can I. And that's crazy because I could hear the audio fine when I did this just before the workshop. But when we did a rehearsal early last week, we couldn't hear the audio either. See, the audio is turned up all the way. I think I know. Let me go back and try this again.
Yeah, there's a
Stop this
setting to
share.
enable share
Yes.
video.
Yeah, optimize share computer sound. Okay, now we'll try it. All right. First of all, we got to get that video. Hold on here. Okay, I think I'm getting closer. All right, share screen. This must be it. The window is invalid. All right. All right, I'm going to try this from the beginning again. Please bear with me. I get rid of that. I'm going to get rid of that. Okay, do that. Back to here, share screen, optimize, share. Okay.
Hello, everyone.
Okay.
My name is Hannah Petersson.
I still don't hear any sound. Do you?
I'm representing the Dutch research organization TNO at this
Yeah,
workshop.
we're getting a sound.
Oh, okay.
If there is anybody here who is familiar with a Dutch accent, then you would hear that I don't have one of those. And that is because I'm Swedish. I'm born and raised in Sweden, the land of Volvo and ABBA and IKEA.
Yeah, I'm glad everyone's getting sound, but me.
With,
so that's
my
good.
master's in space
I've already
engineering
heard
2
it.
years ago. I have some ties to your country as well because I lived in the Bay Area for some time doing my master thesis at NASA Ames Research Center. The topic that I was working on there was tensegrity robotics, and perhaps that can already give you a hint on how we came in contact with you. So I would like to start with thanking you for inviting us. It's a true honor to be here, and we are very happy to be invited. We really look forward to follow your presentations as well, so I'm glad that it will be shared later on and recorded. I also want to thank you for accepting us to record this video, because I think if we do it in real time, it will be around 4 o'clock in the morning for us. So apologies for not being able to be there in real time. I can imagine that you're wondering how we fit into this workshop as well. So I hope that this presentation will answer that question. So I will start with explaining what TNO is, why we are here, talk about our current activities, and then I see that I'm blocking the last text here, but it's explaining what we want to do in the future. So that's what this presentation is going to be about. So firstly, talking about the TNO, introducing who we are. As I already mentioned, TNO is a Dutch research organization, and we have a few thousand employees. The headquarters is in The Hague, as you can see on this picture here, which is about an hour south of Amsterdam. We have a lot of different topics, and for example, healthy living, economy and environment, and traffic and transport. And TNO sort of acts as a bridge within these sectors between university and industry, meaning that we take over projects from the university when their technology readiness level is a bit higher, and they can start to be commercialized, so be a part of industry. and but maybe they are not really fully developed to be actually commercialized yet. So that's sort of where we came into play. The abbreviation TNO stands for Nederlandse Organisatie voor Toegepast Natuurwetenschappelijk Onderzoek. And it's almost impossible to pronounce if you're not a native Dutch speaker. So what it means is essentially Netherlands Organization for Applied Scientific Research. Within the unit industry, we have one part which is about space, and that is also what I am representing. We have our office in Delft, which is close to The Hague, and there are a few hundred people working with space-related projects there. So we have about 55 years of heritage when it comes to telescope development. And for example, the optical tube assembly of the very large telescope in Chile. And that's also what you can see at the background here in the picture. So we developed also mechanisms on board Gaia, for example, which is a European mission set up to map the stars of the Milky Way. I think it was launched in 2014 or something like that, but don't quote me on that. We also have heritage in space instruments, for example, Tropomi. And that's an instrument on board a European Earth observation satellite. So what it does is to monitor pollution in the atmosphere, for example, carbon monoxide and the ozone concentration, to name a few. I don't know if you might have seen these maps of pollution level and the decrease that the current pandemic has had. These are two examples here. So on the upper pictures you can see the situation of the pollution of nitrogen dioxide in March 2018. And then on the lower picture you see the same situation in 2020. You can also see like really in the big city areas, like for example in Los Angeles and on the East Coast, the pollution has significantly dropped. And these type of pictures are taken with the Tropomi instrument that was built at TNO. I should also say that the main reason for this drop is because of traffic, because nitrogen dioxide is generally produced by cars and other type of transportation. With the heritage that we have within telescopes, it seemed like a natural step to go into another domain, which is optical satellite communication, or laser satellite communication. That's the same thing. So this is an area which has been really exploding in the last few years, and our laser satellite communication program started in 2016. So now it has over 20 projects and employ more than 70 people. And we have projects covering ground-to-ground communication, ground-to-space, ground-to-boat, and other sort of more non-traditional laser communication areas. And within this program, we also have a big part focusing on adaptive and active optics. And that's also something we have heritage from the telescopes that we have produced. Traditionally, communication between satellites and Earth has been, and still is, performed with radio frequency signals. But with the recent development in laser technology, and laser communication has been more and more accessible, and the advantages for that are many. For example, the throughput is a lot higher, so that is the amount of data you can transfer. So it's with laser communication in the order of terabits per second, which is quite a lot more than what you can do with traditional signals. Also, a laser beam is harder to intercept because it's simply narrower. And that has advantages within high security sectors such as banking and military and defense, for example. High-end astronomy telescopes, so that's our heritage, usually are extremely rigid, and they are stiff and stable, and they are more usually installed in the fixed locations. And this is also what we have brought with us into this program. For example, a few weeks ago only, we installed an optical communications lab on the top of a tower in The Hague. And I have some pictures here for that. So it's quite a big telescope. It weighs 2,000 kilograms, the whole thing. And the purpose is to provide an infrastructure, so the metrology and operations knowledge and things like that, to develop new projects, and also to facilitate an infrastructure for external customers. But with this new laser satellite communication explosion in mind, the type of telescopes that we have here are not always compatible with that. So there is a need for smaller and more lightweight telescopes. And most often they can also be an advantage if they are transportable. So in other words, a new version of telescopes is considered to be an enabler for democratization of optical communication. And that leads us to the question, do we really need telescopes that weigh as much as a car do? And can we do it easier and better? Our vision is to reinvent the way in which telescopes are designed and built in order to enable disruptive performances and applications. So our approach to this is to redesign telescopes, taking innovative and new concepts in mind, letting go of old constraints such as being located on top of a mountain, having a big optical tube assembly weighing hundreds of kilos, and compensate for the introduced instabilities with optomechanical solutions, such as adaptive and active optics, for example. So within the programs that we have had, we already have good deformable mirrors and fast steering mirrors, etc. So that can be something that we can make use of. In the beginning of this year, our project leader Ivan and I had talking about my background in integrity, and he mentioned that he was looking for something innovative, lightweight, and stable for this purpose of telescopes that we just discussed. So we simply Googled integrity and telescopes and found Don's webpage. And that's really been a source of inspiration and information. And then after that, we talked to Don, and he in turn introduced us to other people in your society. So the reason for us contacting you is exactly this says on the screen, to get inspiration for lightweight and innovative telescope designs. The application areas that we foresee for these kind of lightweight and deployable telescopes, there are quite a lot of possibilities there, both in ground or on ground and in space. So for example, on ground, then you can use telescopes for laser satellite communication, high-end amateur astronomy, exoplanet spectroscopy, because it has a very small field of view, so you can use deformable mirror or adaptive optics to compensate for both atmospheric turbulence and the instabilities in the structure. And generally, you need a small field of view for being able to do both of those corrections at the same time. You can also use it for quantum key distribution, which is used in banking a lot, and defense. And if we look at the space part, then you can also use it for laser satellite communication, for imaging and the quantum key distribution, also for Earth observation, and especially in the field of small satellites. It's quite clear to see why there's an advantage to have deployable and small lightweight telescopes, but that's something that we really believe is going to be even more common in the future, so it's a good area of doing research. These activities that we are performing just started this year, and it's quite a slow process. It takes a long time to do this. But our first task that we were doing was to perform a study and a trade-off to see what kind of technologies that are available at the moment. when you talk about deployment techniques for telescopes, you usually divide them into two primary categories. So the first one is mirror deployment, where you essentially have segmented the primary mirror and then have it in one configuration when it's stowed and then deploy it. And the other category is structure deployment. So the first part of our project was to look into both of these, and an example of the first one, so mirror deployment, is this space telescope that was designed by a PhD student named Dany. He comes from the Technical University of Delft, and that happens to be our neighbor actually. In this case, the M1 it consists of 4 segments which can be folded during launch and then deployed when it is in orbit. And another more high-end example of this is of course the James Webb Space Telescope. So it's a bit of a parenthesis in this presentation, but I'm sure you are all familiar with that, and which is built by NASA, ESA, and the Canadian Space Agency. And I really hope that this will be launched soon. There's been some delays, and I think it's next year is the planned date at the moment. So in the other category of structure deployment, there's a whole bunch of different types of innovative concepts. So taking this as an example, I'm sure you recognize it. It's Don's Tensegrity telescope. It's a lightweight and stable structure. At the moment, to my knowledge, this structure is manually deployable. And you can imagine if we were in a space application, this would be quite difficult. So what we want to do is to use a concept such as this and combine it with other technologies to make it automatically deployable. So, for example, you could use automated telescopic legs, which is close to Brett's design. And looking into more futuristic concept, maybe there could also be combined with inflatable structures, such as this one, as you see. And this is a tensegrity prism with inflatable rods. There are also other options. For example, this kind of hexapod solution. So this is it's tape springs combined with an hexapod. And then you see in the stowed configuration, it's quite compact and small, and then it can be deployed after, for example, when it's used, when it's to be used. And then it can be deployed. So the advantage of having a hexapod as a part of the deployment. The advantage of having a hexapod as a part of the telescope is that you have a quite good means of correcting the secondary mirror. So you have a lot of you can essentially correct all degrees of freedom. And here is a rollable mass concept. The material is sort of rolled up and stored on the spool, and then it can be deployed, and that's something that you also could sort of spin into telescope applications. And then there is another example here, for example, origami folding. So instead of having things rolled up, then you can also have them folded. And then when these are deployed, then you can also use certain rigidization techniques to make them stiff. In case of a space application, then that's quite an advantage, because then you only need to deploy them once. So then after that, you would like them to be stiff. Whereas, for example, in ground, there is a benefit of having it being deployed and then being stowed and then being deployed again. So that's not something that you would use on ground typically. Then we are also looking into different concepts when it comes to metrology. So here you can see a bunch of different concepts. So on the bottom you see the primary mirror, and on the top you see the secondary mirror. And the blue parts that you can see on the first part of the picture, so the first version is actuators, and the red one arrows, they symbolizes sensors. Essentially, it's giving the properties of the allowable properties of the structure, depending on what kind of control strategy you choose. So on the first one, for example, you can have actuators on the M2 and control the position there, but that would require quite a stiff structure because you wouldn't know the absolute position between the M2 and the M1. If we look at the concept underneath it, then you could allow for a bit of a weaker structure, so not that stable, because then you would have a sensor that always monitors the absolute position between M1 and M2, and then you can actuate the M2 to change its position so that you have the maximum performance. If we look at the middle upper picture instead, then you can have actuators on the M1, which would also require quite a stiff structure, because for the same reason as the one to the left, that you wouldn't know the absolute position. And then if you go one step to the right, you could also actuate the structure itself, but that would also mean, yeah, the same conclusion essentially. If we were to implement some deformable mirrors, so the bottom two to the right, then you could have a deformable mirror either as a secondary mirror or a primary mirror. And in the case of, for example, having the primary mirror a deformable mirror, you can allow for a slightly less stiff structure. So this is the kind of trade-off that we are performing at the moment, and we are also matching them with the concepts that we have of deployment, because in some structures are more rigid than others, but with these different configurations of controlling the structures and the mirrors, then you might actually find that a weaker structure but with a better deployment might be favorable over a stiffer structure with another type of control. So coming back to some of the analysis that we have performed, this is some preliminary analysis that we have performed using Don's telescopes as a basis. We were using not exactly the type of or the dimensions that Don has used as his telescopes, but for this version we had the hollow rods, which are the main legs, and they are 10 millimeters in radius with a wall thickness of 0.5 millimeters, and they were used aluminium. It's quite common to use that in space applications anyway, so it's that's one of the reasons. And then the tendons, we used a radius of 1 millimeters, and they are then in steel. The length of the legs are 2 meters, which I think is a bit higher than Don's telescopes are. And then they are 0.3 meters apart. And as a secondary mirror, we used a dummy weight of 2 kilograms. So an analysis that our mechanical engineer John did was to first only analyze the bars. So the sort of legs that are between the M1 and the M2. I'm not sure how familiar you are with this engineering language, but by just having these bars, then the eigenfrequency is 5 Hertz. So that's not very stable. And then what John did was to actually add these sort of tendons and the structure that makes it a tensegrity structure, just to see what the difference is. So then the eigenfrequency actually increased to 21 Hertz. So you can see that it's 4 times better just with this structure, which really says something about the advantage of tensegrity. Then what John did was also to try different sizes of this middle ring. So on the upper one, I think he used a length of 1 meter, and on the smaller one, it's 0.4 meters. And what he found is that it's actually becoming more stable if the ring is smaller, And I believe that this is not conforming with the observations that you have made. So we are really interested in hearing your thoughts about this analysis. And it also really shows the importance of having observations and to actually correlate that with the models that we have to better understand the type of structures. And just as a side note, we really have been interested and sparked, let's say, an interest also as hobby projects. So again, this is our engineer, Jon, who has been building these with his kids in his backyard. And he has not heard of Tensegrity before this project started, but it might be fun to see that it's actually, yeah, it's really fun also. So looking into the future, as I said before, this is the start of the program. So what we have been doing this year is to have a literature study, and by the end of the year we would like to finalize that. We would also like to have a few structure concepts for both ground and for space based on the different type of deployment techniques that we have found. And then we would like to finalize the requirement definition. So that's the, for example, the stability that is required, yeah, etc. So next year we are hoping to really finalize the concept selection. So maybe we have one or more that we want to investigate further, and then we would like to build them and make a prototype to develop them in optimally, let's say, and to test the concepts that we have. So I hope that maybe by the next year, when we have the next workshop, that maybe we can be there in person, and then we have something that, a physical system that we can show. So with that, I would like to thank you for your time, and thank you so much for inviting us. We are available by email, so you can find them on this slide, and Howard told me that the slides will be available to you as well. You have my email address here, and also to our project manager, Ivan Ferrario. If you are interested in any of the things that I have shown you, then you also have a page of references here. So thank you so much, and I hope to hear from you.
Okay, so hopefully everyone both heard and saw the video. I said I couldn't hear it this time, but I was able to earlier. And that wraps up our workshop for 2020. And as I mentioned at the beginning of the session tonight, if you have any questions about Hannah's presentation, to email them to me, and then I will forward them to her and her team, and then they can respond back, and I will post their responses to this group. So if there's any comments or suggestions, I'm real curious on what people think about how doing the workshop via Zoom has gone in general, and how they see us going forward in the future, especially when we're able to meet again in person.
If I may, I'd just like to reflect on the last presentation. Is Dawn Peckham, are you there? Because I'd like to bounce some ideas off of you regarding her findings on the natural frequency of a tensegrity going the wrong way. That was a little surprising.
my goal was to minimize the tension on the strings and minimize the compression of the struts. And so you'd have lower frequency with low force. And they're going to, with the shallower string angle, you're going to have a higher natural frequency.
Oh, so it made sense. Okay.
Yes. Uh-huh.
Got it.
But does frequency relate directly to the stiffness of the structure? Or is it?
It's going to be the tension of the strings. Okay. When the tension of the strings goes up, okay. With a large angle, you have small forces. With a small angle, you have large forces. That's both in the strings and the struts. So my goal was to have minimum forces so you can have smaller diameter struts. Maybe they don't care. I mean, I don't know what their goal is. If they don't care about the stiffness of the struts, then you can have shallower angles and you have higher frequency.
Sure. I think that's part of what was missing from that presentation was, well, they reported on the eigenvalue or the natural frequency and not the actual stiffness or the deflection. So that's important too. You know, if you have a low frequency, but your deflection is really small, then who cares? If you have a high frequency, but your deflection is really big, then that's a problem. So you have to look at both anyway.
Yes.
Okay. Don, way to go. Awesome.
Yeah, I'm really impressed. Like I said, I'm pretty sure this is the first instance of inspiration going from our group out into the professional world. Yeah, that's just a feather in your cap.
Thank you.
Okay, is there any other comments or questions for Dawn and for Hannah and her group that we can include here in the video? Okay, if you think of anything, like I said, send me an email and I will pass those comments and questions on to Hannah and her team.
I think Rachel has
got a
something.
question. Yeah.
Yeah, go ahead.
I have a quick question. Can you hear me?
Yes.
Yes.
I'm helping to write a chapter in a book on amateur astronomy and its implications and everything it's doing. And I just was wondering if it was okay to put in a sentence about this inspiration going from the amateur to the professional world, because that, as you guys are saying, it's not a very common thing. And is that okay?
I don't see why not. I think it's noteworthy.
Yeah, it seems very noteworthy. And okay, cool.
Yeah, that's exciting too. Yeah.
Yeah.
Do you have a title for your book?
Well, I'm just helping write the chapter on amateur astronomy, and it's about engagement with the public.
Okay.
It's a whole book on astronomy. There's chapters on citizen science and everything. I will definitely send a link when we get an actual book.
Oh, good. Okay, thanks.
Yeah.
Thank you very much. That's awesome. All right, anyone else?
I think the Zoom format was a huge success. It enabled me to cook dinner while I was listening in. Thanks. But I sure wish we could all be in person, of course.
Well, yeah, we certainly missed the social interaction, the barbecues, and just the hanging out in the workshop atmosphere. That's something that we can't capture any other way. I'm personally really gratified with how it's turned out, and I'm really relieved that I haven't totally screwed it up on my end by being the host. So if nothing else, it just goes to show how easy it is to do this via Zoom.
That social
I'll
aspect.
sleep well tonight.
I think everybody wants to put their hand on Don's controller and move that scope.
Oh, it is a treat. It is really a treat. It has come really, we could do a whole workshop on his telescope. It is so feature rich and so innovative. I think in his earlier presentation a couple days ago, he showed a very short video driving his telescope through the snow. Now, I'm sure that is the first time a telescope has been driven through the snow on its own little tractor tread. So, yeah, so it is worth a lot more inspection and discussion in the future for sure.
I'd like to point out something about the clutch system. About 4 years ago, when I first took over the job of writing the Astronomer's Workbench column for Sky and Telescope, one of the very first things I wrote about was about a very rudimentary mechanical clutch system using a bicycle clutch or a bicycle brake lever and
I remember that, yeah.
a set of jumper cable clamps on the altitude bearing as the actual clutch. And I just like to point out we've come a long way thanks to Ed. I think perhaps we should revisit that in another article at some point in the future.
Oh yeah, absolutely.
So Howard, this is Joe and Squim.
Hey, Joe.
Hey, if anybody noticed a name up there, John Martinez, and wonders who that is, it's a friend of mine that I invited in. And Russ, Genet, are you there? Russ knows John very well. John worked with Les Cumbres Observatory in Santa Barbara for 7 or 8 years, I believe. And oh, there he is, right there.
Yeah. Russ has his microphone turned off, but
Turned
he's
off,
logged
okay.
in.
Yeah. So John's in New Orleans, Louisiana, and I invited him in because he knew Russ, and I don't think he knows anybody else actually. But anyway,
Nice to meet you, John.
Yes, I really enjoyed the presentations. I was hoping to say hi to Russ, but looks like he's off right
Well,
now.
his microphone's off. That doesn't mean he's not there. He
probably
could be
trying to
having a
turn it
cup
on.
of coffee or something. Who
Right,
knows?
right. But it seems like you've got a lot of material that would be great content for intermediate Zoom conferences between the two big annual meetings. So you are looking for interesting ideas to continue Zoom work. That I think you've got a lot of material for topics.
Oh, yeah.
Yeah,
I
like
agree.
Ed's telescope, for instance, could
Yeah, we
occupy a
could just
couple
have a
of,
whole
meetings.
symposium on him. Yeah.
Right.
And frankly, I want to get that T-shirt that he has. You can't buy happiness, but you can get a telescope, and that's the same thing.
Right.
That's what I want.
And
have a-
yeah, maybe one day I'll get
feature
up
of
to
the
the
month.
Oregon meeting and
That'd be awesome.
see what you guys are up to. I haven't really been active with Les Cumbres Observatory anymore since I left in 2014. But they're doing well. They have all their robotic telescopes deployed now around the world, which I'm kind of proud to have been part of. And they've generated, gosh, I don't know how many papers now on exoplanets and active galactic nuclei, supernovae, all sorts of things.
and John also has his eye on the Tulane Carver telescope. If anybody remember, it was 13-inch, was it?
Yeah, that was a telescope that was actually used by Pickering.
Right.
And he discovered one of the moons of Saturn with that telescope. I think it was Phoebe, maybe. But that telescope is now in storage. And it's a shame that it's not on display. I've been working to try to remedy that situation, but administrators don't really seem too interested in
Oh, good
thinking
luck.
about it. But it was used in Jamaica. I think Harvard had some involvement with it at one time. It ended up at the Cunningham Observatory on the Tulane campus in New Orleans. And then that building got torn down and the telescope was put in storage.
Yeah, that's a historic telescope. So, all right.
Yeah.
Oh, heck yeah.
Yeah.
So that telescope would be a talk.
No doubt.
On its own, and it's a telescope that I first used when I was 17 years old.
You know, we very often have a talk based on some aspect of astronomical history as part of the workshop.
Right.
We didn't this year, but if you would be willing to talk about that telescope for next year's conference, that would be awesome.
Yeah, we can come up with something. If not that, something else.
Okay.
Maybe some of the work we did at Las Cumbres.
Are you familiar with the Antique Telescope Society?
I'm sorry?
Are you familiar with the Antique Telescope Society?
A little bit. So is Joe LaCour.
I remember.
I forget the name of the guy that's really involved with that. Joe, what's his
Ken
name?
Lonnie?
Yeah, Ken Lonnie. In fact, he acquired a couple of the small refractor telescopes that were
that's
also
right.
involved with the Calver telescope at the old Tulane Observatory. But this is a monster telescope. I mean, it's like 2,000 pounds of telescope. It's all cast iron tube. It's just awkward and heavy.
It's a reflector?
It's a reflector. It's a 13-inch f10 Newtonian on an equatorial mount. And the original configuration used a gravity drive, which is now missing. Not sure what happened to that. And it was replaced with an electronic drive system many, many decades ago.
Yeah.
But other than that, it's still in pretty much original condition.
I can imagine Dan is thinking how easy it would be to put a SciTech system on that thing.
Always thinking about that.
Oh yeah. Okay.
It's probably most valuable in its current antique condition, just as a historical artifact. So.
Yeah.
But anyway, I enjoyed the few hours that I had tuning in on your activities here.
Okay. Well, you just got the final session. We had 3 earlier sessions the last 3 days, and the
I tuned in a bit
recordings.
yesterday too.
Yeah, the record. Okay, then we do have the recordings. Joe can probably forward the links to those if you'd like, so you could see the whole thing. There's some really good presentations every day. There
Right.
wasn't a slow day at all. So I'm curious again about just maybe more comments on how we move forward again when we can meet in person. We talked a little bit yesterday, I think, about when we've done this in the past and we've met in person, that we never recorded the talks. All the presentations are gone, and there are some really excellent things that are just lost to history or a deck on somebody's hard drive somewhere, and the world doesn't have access to it. So what I'd like us to do, hopefully next year when we're meeting in person, is to be able to combine the personal aspect, but also recording the sessions so that we can archive and share what we're doing with the world. Because I think what we're doing is really valuable, as evidenced by Don's work and what he's inspired. So I don't know the technical answers to that. I'm sure it's fairly straightforward. Before I got into looking at doing this on Zoom, I was a complete neophyte, and as such, I was pretty nervous about it. Now it seems pretty straightforward, so it's just a matter of finding a good method or methods to move forward and plowing ahead. But if any of you have any thoughts now, that's great. Think about it, get back to me later. We have lots of time to get ready for next year.
Yeah, it'd be good to have a combined one where some people that didn't want to travel could also phone, so it would get recorded. So it'd be a Zoom plus, a few of us could meet over in Portland, because I can drive.
Exactly. There's a lot of people who can come to Portland, but there's many, many more people around the world,
right,
who could participate online by giving presentations or just tuning in to hear the live presentations. So yeah, that's my hope for this, is that we're able to make this more of a worldwide event, as opposed to mostly West Coast US type of an event.
Cool.
Yeah, because we got some great ideas, but there's a lot of great ideas out in the world that we don't know about. No question.
So I'm just really glad that you picked this up, Howard, and took this to the Zoom, since we really can't do it practically in person. So thanks so much, Howard, for doing all this work
my
and
pleasure.
figuring all this stuff out and getting it. And also thanks on my presentation on Thursday night. I'm telling you, I'm just really, really thankful for the input that I got from everybody here. Joe, did you hear my talk, just my 5-minute talk?
Yes.
Yeah, good. And how about you, Rob? Rob's gone now.
Yeah,
Rob?
his microphone's turned off.
I'm here. Yeah. Did I hear your 5-minute talk?
Did you hear my 5-minute talk right at the end of the FIRO presentation?
Oh, I'm sorry. I had to miss that.
Oh, okay.
It was
That's all
dinner
right.
time.
Okay.
Yeah.
Yeah,
too bad.
yeah, I understand. All right. Anyway, I got a lot of input on my talk, and I really, really appreciated it. And it's going to make it a better project. So this is really good stuff. And what Don did and what they picked up, and now they're using it. That's pretty cool too, Don. And Ed, you're, gosh, you're a little bit crazy, I think. Like probably most of us.
Oh, well, yeah,
That works
we're all
out
half
good.
nuts, that's for sure.
And Marty, it's nice to see you. I know you haven't been very active here, and I'm going to see you soon for sure. So.
Howard, you mentioned historical astronomy. Have you heard about Joe LaCour's replica of the Gascoigne micrometer?
Yeah, I did
Oh yeah, he gave a
Okay.
presentation on that
Okay,
at a
right.
past
Couple years
I
ago.
thought he
workshop.
had, yeah.
Oh yeah, and it was a beautiful instrument what he recreated.
And the other one, the one that I made for David Sellers, who wrote the book on Gascoigne in Leeds, up until the COVID, he was touring around with it and giving talks. And I think the Leeds Museum made a replica to display over there. So if anybody gets to Leeds, it is in the museum there for William Gascoigne.
All right, very cool.
And Dan, I'd sent you that stuff on the LIGO paper. You can read that little thing I wrote up, the lessons learned.
Yeah, I saw all the
about
pictures.
the coils. Yeah, I sent you the report.
Yeah, I saw all the pictures. I haven't finished reading it yet.
Yeah, the report is you might get something out of about winding coils.
Yeah, I would like that. Oh, I also wanted to mention, Rachel, I like your cat.
All right. Okay, everyone. I'm reluctant to say goodnight.
Let's see your cat one more time.
Oh yeah, okay. Let's see Rachel's cat.
She's not in the room right now. Sorry.
Okay. Cat's gone.
Hold on just a second.
You have a cat, Jerry? Companion cat?
I have an emergency backup cat.
Oh, there you
Okay,
go.
good. Yeah. We have one, but I'm not on a laptop, so I don't have my camera on. That's funny.
Okay. Yeah, 'cause normally this would be the time when we'd all get a cold beer out of the cooler and maybe chew on a cold piece of leftover chicken from the barbecue at lunchtime. So it feels awkward to call the workshop at this point. But unless anyone has some really interesting and fun ideas, I think this is probably it for this year.
Yeah, that's good. It was great. Dan.
Oh, there you go. Dan's got the cold beer. All right, chug it, Dan.
Already
Drink it for the whole group.
I'm not a chugger.
Dan, that's why I sleep on your office floor, so I can have a beer the Saturday evening, or Friday evening.
Okay. Good going.
Cheers, everyone. Thank you, Howard. Good night.
Okay.
Good night. Good night, Howard.
Good night, everyone. Thank you very much.
Good night. Thank you.
Okay.
Thank you.
See you around.
See you next time.
Thank you so much.
Good night, everyone.
for your
You're
work, for your
welcome.
help. Howard, bye.
Bye. Bye, everyone.
Bye, everybody.